Hello everyone. Am I audible? Audio video is okay? Audio video is okay? Please reply. Okay. Okay. Now it is okay. So now we can proceed. So today I am going to discuss organic chemistry, mainly class 11th part. Okay, we start with alkane chapter. In alkane, we start with this methods of preparation. Okay. In methods of preparation, alkane general formula you are knowing, and alkane general formula is what? CnH2n plus 2. This is general formula of alkane, and they are also known as paraffins. Alkanes are also known as paraffins, and why they are called as paraffins? Because they are less reactive. They are having very less reactivity. So sometimes they can ask why alkanes are known as paraffins. Answer is because of their low reactivity. Because of their low reactivity, they are known as paraffins. Okay, come to the methods of preparation. Most important reaction, Wurtz reaction. What Wurtz reaction is? We are taking alkyl halide, for example RCl, and it is treated with sodium in the presence of dry ether. In the presence of dry ether, it is giving product RR. What is the actual mechanism there? RCl is going to give R radical. It is going to give R radical. Two mechanisms are there. I am explaining by one. Another one more R radical is formed. Means I can consider 2 moles of RCl generating 2 R radicals. These R radicals are going to combine. You must know one thing. If radicals are there, they have tendency to couple. One radical, another radical. These two radicals, they have a tendency to couple. They are having tendency to combine. So what will happen? RCl, I am taking 2 moles of RCl. This is giving R radicals. They are going to combine, and after combination, we are getting what? RR. Now in this case, solvent is very important. In this case, we are using dry ether. Means condition must be dry. We cannot use moist ether. We cannot use water. This reaction we have to proceed in dry ether conditions. What is the important thing there? RCl reacting with sodium giving RR. Okay, this is what Wurtz reaction. Now, let someone is saying to prepare CH3, CH2, CH2, CH3. Means someone is saying to prepare normal butane. So how we can prepare? Now, if you observe, this is what? This is a 4 carbon. We have to select this fragment. So what will happen? This left side and right hand side, both are having 2 carbons. Na? So it becomes symmetrical condition. So it is better to select this CH3, CH2, Cl. Treat with what? Treat with sodium dry ether. Treat with what? Sodium dry ether. You will get this product by Wurtz reaction. Okay. But in this case, if someone is saying to prepare CH3, CH2, CH3 by Wurtz reaction. Someone is saying to prepare CH3, CH2, CH3 by Wurtz reaction. So in this case, if you select any fragment, let's say I'm going to select this fragment. So left hand side having 1 carbon, right side is having 2 carbons. Means we cannot get symmetrical condition there. Left side 1, right side 2. In this case, if I select this left hand side 2, right side 2. But if I want to prepare this, one side we have 1 carbon, other side we have 2 carbons. We cannot get symmetrical condition there. So we are going to select this one, CH3Cl for this part. And for this part, I am going to select what? CH3CH2Cl. Reaction condition is same, sodium dry ether. What will happen? We can say this CH3Cl, ClCH3 combine by Wurtz reaction like this sodium dry ether. What will happen? This is Cl. Okay, so what will happen? CH3CH3 is formed, one possibility. Another possibility, CH3CH2Cl combined with another molecule of same CH2CH3Cl and sodium dry ether is there. What will happen? Remove NaCl, one more product will form CH3CH2CH2CH3 and these two combine. What will happen? This product is formed. So what we can conclude, if you want to prepare symmetrical alkane, by Wurtz reaction, it is easy to prepare. But if you try to attempt to prepare unsymmetrical alkane, you will get multiple products. That is why we can say Wood's reaction is not preferred. Wood's reaction is not preferred for the preparation of unsymmetrical alkanes. Listen carefully one more time. Let you want to prepare symmetrical alkane. Let you want to prepare symmetrical alkane. We can easily go for Wood's reaction. We will say take this one. Obviously 2 moles of this will react. What will happen? Sodium diether giving only this product. Is it okay or not? But if you want to prepare unsymmetrical alkane, then you have to select these 2 halides. What will happen? These 2 combining giving this. This same molecule, one more molecule of same is going to combine, giving one more product, 4 carbon. One more molecule of this is going to combine. What will happen? Giving this product. Means you are trying to prepare this and you are getting these 2 also. It means you are not getting this only, na? That's why I am saying Wood's reaction is not preferred for the preparation of unsymmetrical alkanes, but it can be preferred for preparation of symmetrical alkanes. Okay, one more thing. In Wood's reaction, what we are observing, R is formed. Mean this side is carbon, for example CH3, this side also CH3. For example, we select simplest alkyl halide CH3Cl. Simplest alkyl halide CH3Cl. Treating with sodium in dry ether. What you will get there? CH3. You will get this molecule. How many carbons are there? 2. Means by Wood's reaction, what we cannot prepare? By Wood's reaction, what we cannot prepare? We cannot prepare CH4 molecule by Wood's reaction. This is a very important point there. We cannot prepare CH4 molecule by Wood's reaction. So 2 important things are there. First thing, Wood's reaction is not preferred for unsymmetrical. Wood's reaction is not preferred for unsymmetrical. And methane CH4 cannot be prepared. Is it okay or not? So 2 things are very important. And don't get confused. For unsymmetrical, Wood's reaction is not preferred. Means it can be prepared, but it is not good method. For methane, you cannot prepare by Wood's reaction. Okay, come to next one. Now we have RCl treating with zinc, one condition, treating with zinc H+. So what is the chemistry of zinc dust? Zinc is hungry for 2 halogens. Remember one thing, zinc is hungry for 2 halogens. So it will say, you are giving me 1 halide, monohalide is given. You are giving RCl. Only 1 chlorine is there, but I am looking for 2 halogens. Why looking for 2 halogens? It is trying to react with 2 halogens and giving ZnCl2. That's why it is hungry for 2 halogens. So what we can say? Zinc will say, you are giving me monohalide, but I am hungry for 2 halogens. It is having only 1 halogen. So what will happen? 1 zinc will react with 2 RCl to remove ZnCl2 from there. What will happen? You will get R. One condition. So first will give you what? RR. Second condition, what is given? Zinc with H+ is given. This is different. Only zinc and zinc with H+, both are different. Zinc with H+, what will happen? It is going to give RH. For example, let we have this one, CH3, CH2Cl, treating with zinc dust. What will happen? Zinc is looking for 2 halogens. It is a monohalide. What will happen? It will react with 1 more molecule of same. What will happen? ZnCl2 we have to remove. What will happen? They are going to combine. You will get 4 carbon alkane. But if you treat same molecule, let's say this same molecule I am writing there, CH3, CH2Cl, treated with zinc in the presence of H+, what will happen? This is going to give CH3, CH3. This is going to give what? CH3, CH3. Means simple thing is that what I said, if you are taking RCl, with zinc, it is giving RR. But RCl with zinc H+ giving RH. Okay, clear? Next. Decarboxylation reaction. Now name is the answer. Decarboxylation means removal of carboxylic group. For example, you have carboxylic acid RC double bond OH. For decarboxylation, what reagent we are using? Soda lime, NaOH plus calcium oxide heating. What we are using for decarboxylation? NaOH CaO heating. What will happen? Now, if you observe sometime, they will write this also, so RCOO minus Na plus. Why? Because medium is basic now. NaOH we are using there. So if we are using carboxylic acid, that will convert into carboxylate. Now, what is the trick there for decarboxylation reaction? Whenever you are observing NaOH CO, soda lime with heating, remove this carboxylic group completely. Remove this carboxylic group and satisfy the valency by hydrogen. What product will form? RH will form. What product will form? RH will form. Okay, for example, we'll select some examples you will understand. For example, let's say this is given CH3. I am not writing hydrogens, I am writing only carbon. Let's say this is given. Let's say this is given COO minus Na plus. One example. Second example, this is given C double bond O minus Na plus. Third example. These are given. All are heated with soda lime. Soda lime heating. Soda lime heating. Soda lime heating. What is our trick to find the product? What is our trick to find the product? Remove this group and satisfy the valency by hydrogen. So if I remove this group, what left? 2 carbon left now, means this product will form. CH3 will form. In this case, remove this group. Remove this to satisfy the valency by hydrogens. What left? This part left now. 4 carbon. In this case, remove this group and satisfy the valency by hydrogen. So this part left, you will get this product. Is it okay or not? So what is the thing? What is the trick for decarboxylation reaction? COO minus Na plus group is there. Remove that group and satisfy the valency by hydrogen. Remove the group and satisfy the valency by hydrogen. Identification. What is the identification for decarboxylation reaction? They will give you carboxylic acid or they will give you sodium salt of carboxylic acid. Reagent will be what? Soda lime, NaOH CaO. One more theoretical question they can ask based on class 12th NCERT, that in what proportion we are using NaOH and CaO. In what proportion we are using NaOH and CaO in decarboxylation reaction? Answer is 3:1. It is in class 12th NCERT. Clear or not? So this is what decarboxylation reaction. Next is what? Coal-based electrolysis. Next is what? Coal-based electrolysis. It is also for sodium or potassium salt of carboxylic acid. We have this sodium salt of carboxylic acid. It is going for electrolysis. It is going for electrolysis. What the trick? What is the trick there? Remove this group and make a radical. Remove this group, make a radical. Whenever they are giving electrolysis, remove this group, make a radical. Now you are knowing if radicals are there, they have tendency to couple, they have tendency to combine. So write one more radical, combine both of them. What product is formed? RR is formed. Means story is same as Wurtz. RR is formed now. Story is same as Wurtz. Means in this case also you can say methane cannot be prepared. Methane cannot be prepared and it is not preferred for R prime R, means unsymmetrical alkanes. I am not saying it cannot be prepared. I am saying it is not preferred. Is it okay or not? Now I will combine both reactions, means Wurtz as this coal-based electrolysis and decarboxylation, and we'll try to solve few questions. For example, let's say this is given. Let's say this molecule is given COO minus Na plus. One condition, they are giving soda lime NaOH CaO heating. One condition. Second condition, they are saying electrolysis. Follow the trick, you will get answer. Follow the trick, you will get answer. What is the trick for decarboxylation? This is decarboxylation, reason for decarboxylation reaction. What is the trick there? Remove this group and satisfy the valency by hydrogen. Now count carbon. 1, 2, 3, 4, 5 carbons. This group is removed. Na? This group is removed. After removing, what left? 1, 2, 3, 4, 5 carbons left. So we will get 5 carbon alkane. 1, 2, 3, 4, 5 carbon alkane. Now this is given. Electrolysis is given. What trick is there? If electrolysis they are writing, remove this group. Same way we have to go for this also. Remove this, but make a radical. Remove this, but make radical. Now one radical is formed, so we have to take one more molecule of this. So one more molecule we have to take. Combine two radicals. Radicals have tendency to couple. Then radicals have tendency to get coupled. So what will happen? 1, 2, 3, 4, 5 carbon in this radical. One more radical with 5 carbons. So total carbon count will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Understood not? This is clear or not? So this is the way to solve decarboxylation and coal-based electrolysis. I'll take one more example. Let's say this is given. COO minus, COO minus, Na plus, Na plus. One condition examiner is saying NaOH CaO heating. NaOH CaO heating means decarboxylation reaction. Another condition examiner is saying electrolysis means coal-based electrolysis. How to find the product? What is the trick there? What is the trick there for this reaction? Remove this group, satisfy the valency by hydrogen. So what left? 1, 2, 3, 4 carbon. So 1, 2, 3, 4 carbon means 4 carbon alkane is formed. 1, 2, 3, 4 carbon alkane is formed. Is it okay or not? Come to this one. Electrolysis. What is the trick there? Remove this group, make radical. Remove this group, make radical. So what you can observe there? You can observe two radicals present in same. Two radicals present in same. So in this case, we don't need another molecule. No? But two radicals present in same molecule. So why we are dependent on another? This molecule is itself sufficient enough to couple them. Understood not? So what will happen? These two radicals are going to make bond there. In this case, it is not dependent on another. So what product will form? You will get double bond there. This become double bond. Is it okay or not? This is what electrolysis reaction. Let's take one more example for more clarity. Let's say this is given. This is given COO minus Na plus, COO minus Na plus. One condition examiner is saying NaOH CaO heating. Second condition examiner is saying electrolysis. This is the best way to understand both the reactions. We have to read both the reactions together, because in both the reactions means decarboxylation and coal-based electrolysis. In both the reactions, substrate is same. Okay, so what will happen? What will happen in this case? What is the trick there? So this decarboxylation reaction, remove this group, satisfy the valency by hydrogen. So what left? This part left, na? 4 carbon, 1 double bond. What left? We have this product. Come to this one. Now they are saying electrolysis. What is the trick there? Remove this group, make radical. Remove this group, make radical. So what we can observe there? Now in this case, what we can observe that two radicals present in same molecule. What will happen? They are going to combine. What will happen? Now double bond is there. One more bond is formed. So this becomes triple bond. You will get this product. No? Carbon, carbon, carbon. I am not writing hydrogen. So what is the difference there? Between monocarboxylic acid and dicarboxylic acid? If you have monocarboxylic acid, for example, this is there. What will happen? In case of electrolysis? If it is monocarboxylic acid, we have one radical, R radical. Mono radical is there. So it is dependent on another. Two radicals are going to combine. But if two radicals present in same molecule, for example, in this case, what will happen? In this case, two radicals present in same. During electrolysis, it is not dependent on another. What will happen? They are going to combine and they are going to form a product. Okay, so let's solve one more question. This is given. Solve this question, please. One condition, NaOH CaO heating, soda lime heating. Second condition, electrolysis. Solve this question. Okay, I think done. What will happen in first case? What is the trick there? Remove this group, satisfy the valency by hydrogen. Remove this group, and now how many carbons are there? First of all, count them. 1, 2, 3, 4, 5. Remove this group, satisfy the valency by hydrogen. Remove this group, satisfy the valency by hydrogen. So what will happen? 1, 2, 3, 4, 5 carbon. 1, 2, 3, 4, 5 carbon. Pentane is formed. Come to this one, electrolysis. What is the trick there? Remove this group, make radical. Remove this group, make radical. So what we can observe there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Radicals are formed now, and what you can observe there? Two radicals in same molecule. What will happen? They are going to combine. So what will happen? 1, 2, 3, 4, 5. 5-membered ring will form. Understood the difference or not? This is clear. This is about decarboxylation reaction and electrolysis. Come to next, catalytic reduction. Catalytic reduction means what? Let's say we have this alkyne RC triple bond R, or we have alkene RCH double bond CHR, and we want to convert this into alkane RCH2CH2R. So simply you can say, if you want to convert alkyne or alkene into alkane, hydrogenation is required. Addition of hydrogen is required. So for this reaction, what is the reagent there? Hydrogen. But direct reaction of hydrogen and alkyne or alkene is very slow. It is not giving alkane with good yield. So some catalysts are required. And in this case, what catalyst we are using? Nickel, palladium or platinum. What we are using? Nickel, palladium or platinum. So hydrogenation in the presence of catalyst is known as catalytic reduction. What will happen? Alkyne or alkene react with hydrogen in the presence of NiPDPT, giving alkane. Very simple reaction. Next one, chemical properties of alkane. Most important reaction of alkane is what? Free radical substitution reaction. Most important reaction of alkane is what? Free radical substitution reaction, or you can say this is the characteristic reaction or main reaction of alkane, and that is what? Free radical substitution reaction. Now come to the example. Let's say this is given CH4. CH4 is given. It is reacting with Cl2. Reacting with Cl2 in the presence of light. In the presence of light, they will represent like H nu. H nu means photon. So presence of light, they can directly write light, UV light or diffuse sunlight like this, or they can write H nu. This is the identification there. Cl2 H nu means free radical reaction, free radical substitution reaction. Okay, now we have to think about the products. So what will happen? Now this free radical reaction, this is free radical substitution reaction reagent. This is going with 3 steps. 3 major steps are there: chain initiation, chain propagation, and chain termination. Okay, chain initiation. Chain initiation means what? Cl2 is there in the presence of light, or sometimes they can give you high temperature also. They can give you high temperature. You must know one thing: presence of light and high temperature are the favorable conditions for radical reactions. Presence of light or high temperature are the favorable conditions for radical reactions. So what will happen? They can give you light or they can give you high temperature. What will happen? Due to light or due to this photon, what will happen? This Cl2 is going to break homolytically. If homolytic bond fission is there, what will happen? Cl radicals are generated. Cl radicals are generated. What next? This CH4 molecule is there. It is going to combine with Cl radical. What will happen when Cl radical combine with this CH4? It is going to combine with, so this CH4 I can write like this, CH3H. So this Cl radical is going to combine with H of this CH4 molecule. If it is combining with H of this CH4 molecule, what left there? CH3 radical left. So what we get there? CH3 radical plus HCl. This is formed. Then this CH3 molecule, CH3 radical will combine with Cl2 molecule. CH3 radical combine with Cl2 molecule. When CH3 combine with this Cl, what will happen? CH3 Cl combine. What is formed? CH3 Cl is formed, and this Cl radical is generated. Now this Cl radical can react one more time, so we can repeat this reaction multiple times. This is propagation. Second is propagation. Third process. What is formed there? Cl radical is formed. CH3 radical are formed. So what will happen? Radicals are going to couple. This is termination. For example, Cl radical combined with Cl radical. What will happen? This is formed. Cl radical combined with CH3 radical. This is formed. And one more and the most important one, CH3 radical combined with CH3 radical. CH3 radical combined with CH3 radical. What will happen? CH3 is formed. Okay or not? And this is a byproduct of this reaction. And why it is important? Why it is important? Let's say examiner is saying during the chlorination of methane, what are the possible products or what is formed there? Answer: one hydrogen displaced by chlorine, CH3Cl is formed. One more hydrogen displaced by chlorine, CH2Cl2 is formed. One more hydrogen displaced by chlorine, CaCl3 is formed. One more hydrogen displaced by chlorine, CCl4 is formed. So these four products anyone can guess. Anyone can guess. Now, by chlorination reaction, common sense here, remove hydrogen, bind chlorine, remove hydrogen, bind chlorine. These four products anyone can guess. Those who are knowing basic fundamentals of chemistry, they can guess. But one more product is formed, that is CH3. This is a very important. This is a byproduct and it is very important. Is it okay or not? Why this is very important? Let examiner ask which of the following product is not formed. Which of the following product is not formed during chlorination of methane? First option this, second option this, third option this, and fourth option none. Answer will be none, because all these are formed. Why I am emphasizing on this molecule? Because they will say term chlorination of methane. They will use term chlorination of methane. At that time, every student will running towards chlorinated product. Everyone will say chlorine is there, yes it is possible. Chlorine is there, yes it is possible. This is not possible. In reality, this is also formed as byproduct. That's why I explain mechanism. Otherwise, very few fundamental things are there to identify the mechanism. If radicals are generated, it is initiation. If radicals are generated by molecule, it is chain initiation. If one is radical and one is a molecule, or one is a radical, another is a molecule. One radical like this one, this is a radical. One is a radical, one is a molecule. One is radical, another is molecule. Means radical molecule is there, it is a propagation. Radical molecule, propagation. This is the identification. And if two radicals are going to combine, termination. Once radical get combined, chain get terminated. Common sense here. This is the identification. What are the identifications there? Radical is generated, initiation. One is a radical, another is a molecule. One is radical, another is a molecule, propagation. Two radicals combine, termination. So one more question they can ask: byproduct of the chlorination of methane is ethane, which is formed in, answer, chain termination step. Listen carefully. Byproduct of chlorination of methane. Byproduct of chlorination of methane is ethane. It is formed in, first option initiation, second option propagation, third option termination, fourth option it is not formed. What is the answer there? It is formed in chain termination step. This is okay or not? And one more thing, how to identify is clear or not? Now, one more thing, they will give you condition like, let's say this is given CH4 plus Cl2 CH4 Cl2 H nu is given, CH4 Cl2 H nu is given, and you have to tick only one option. You have to tick only one option. You will prefer CH3Cl. You have to prefer CH3Cl. Now, let's say they are saying CH4 is present in excess. Definitely this you have to tick. If they are saying Cl2 present in excess, then multiple products we have to tick. If general they are saying, we have to tick all possible products there, because in radical reactions, all possible products are formed. If all are given in the option, if these are given in the option, then we have to tick all. Is it okay or not? Next, isomerization reaction. Isomerization reaction. Reagent is very important for this reaction. Reagent is, and one more point, in case of free radical reaction, sometimes they are asking possible monochloro products. For example, I will select isopentane molecule. They will give you isopentane is there treated with Cl2H nu. They can give you Br2H nu. They can give you I2H nu. Cl2H nu is given, and they will ask how many monochloro products are formed. Monochloro products. Why they are emphasizing on monochloro? Because you are knowing that multiple products are possible. Now, how many monochloro products are formed? They will ask this question. For example, this is given. This is given. So how to find? In this molecule, think about the different type of hydrogens. For example, this hydrogen and hydrogen attached to this carbon and hydrogen attached to this carbon, they are same, na? They are identical. They are identical. Hydrogen attached to this carbon and hydrogen attached to this carbon, they are identical. So use similar symbol. So I can say this hydrogen, they are identical. So I am using similar symbol. This hydrogen is not matching with these two, means this is different. This is different. So use another symbol. This is also not matching with any of these two, means this is also different. So use one more different symbol. Come to this one. This is not matching with any of these three. This is also different. So again use a different symbol. Let's say I'm using this symbol. It means we can write 4 different structural monochloro products. For example, for this symbol, what we can write? For this symbol, we can write this product. For this symbol, we can write this product. For this one, you can write this product. And for this one, you can write this product. So now, if examiner is asking how many monochloro products are formed, then don't directly answer 4 for this example or for this question. Why? Because they are not mentioning structural isomers only. They are saying how many monochloro products are formed. Then we have to check stereo centers also. For example, in this first case, chiral carbon is there or not? Yes, it is there. This is chiral carbon. So what will happen? Due to this chiral carbon, one more will be there. That will be its mirror image. So for this, I will say 2 are there. One is this, one will be its mirror image. In this case, nowhere chiral center is present, means only one is possibility. In this case, this is a chiral center. CH3, Cl, this entire group and hydrogen, all 4 are different. This is chiral center, means this has 2 possibilities. In this case, no chiral center, means only one possibility. So how many monochloro products are formed? For this isopentane, 1 plus 2, 3 plus 3, total 6 monochloro products are formed. Now, 2 type of questions will be there. One question, let's say this is given, isopentane is given, examiner is saying how many monochloro products are formed. Your answer is 6. Why? We have to consider structural as well as stereo center also. Second question, let they are asking how many structural monochloro products are formed. Structurally different monochloro products are formed. Then answer will be 4. 1, 2, 3 and 4. We have to ignore stereo center then. Third question, let's say they are asking how many monochloro products are formed for isopentane. And 6 is not there in the option. 6 is not there in the option. Then what you will tick? You will tick 4. Means at that time you are considering structural isomers only. Clear or not? So let's solve this question. Now I am taking normal pentane. Solve how many monochloro products are possible. How many monochloro products are possible? Done? Solved? Okay. Okay. Now in this case, these two carbons are identical. So I am using same symbol, identical symbol. These two are also identical but different than these two, and this is also different one. So means we can write three possible structures for this symbol 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and this Cl is there. Another one. These three you can write. Now check stereo center. In first case, anywhere chirality is there or not? Chiral center is there or not? Answer is no. Second case, yes, this is chiral center. So two possibilities for this, only one for this one. In this case, anywhere chiral center is there? No. So only one possibility is how many? 1 plus 2 plus 1. Answer is 4. Answer is 4. This is okay. Now next one. Isomerization. For isomerization reaction, what is the reagent there? Reagent is AlCl3HCl. What is the reagent there? AlCl3HCl. This is the reagent. Now, for example, I am taking hexane, normal hexane. 1, 2, 3, 4, 5, 6. Normal hexane I am going to take. Normal hexane is heated in the presence of AlCl3HCl. So what will happen? What will happen? Multiple products will form. Multiple products will form, but we have to focus on major products. You are knowing in organic chemistry, our main target is major product. Because while organic reaction, in most of the cases, you will find so many products are formed. But our main focus is on major product. So now, what is there? We are using normal hexane treated with AlCl3HCl. Treated with AlCl3HCl. This is the identification. AlCl3HCl heating isomerization reaction. Isomerization reaction for alkane. For alkane. Now, how to find major product? Very easy. If they are giving 6 carbon chain, major product will be having 5 carbon chain. How to find the major product of isomerization? Let they are giving 6 carbon chain, major product will be 5 carbon chain. They are giving 6 carbon chain, major product will be 5 carbon chain. So 6 carbon chain is given, major product will be 5 carbon chain. But total carbon count is 6 na yaar. It is a 5 carbon, means 1 extra carbon left. Now let's assume this is 1 extra carbon. So what are the possibilities? What are the possibilities there? Extra carbon you can bind at this place. One possibility. Extra carbon you can bind at number 3. This is another possibility. And don't say, sir, please bind extra carbon at this place. This is not isomerized. This is same molecule which is given in the substrate. Same layer 1, 2, 3, 4. Normal hexane, normal hexane. So don't say to bind at this place. Okay. So now what we can observe there? What is the trick there? 6 carbon is given in the chain. Major product is having 5 carbons in the chain. So with 5 carbons in the chain, we have 2 possibilities for that 1 extra carbon now. What are the possibilities? You can bind at number 2 and you can bind at number 3. Don't say to bind at 1. It is same substrate, hexane. So these 2 major products are formed. Minor products are so many, we have to ignore them. But don't say only these 2 products. So some more products are formed which are not important. More products are formed which are not important. This is done. Come to next one. Aromatization. Very important reaction. Aromatization reaction. Very important. Very important. What is the reagent for aromatization reaction? Very easy to memorize. Oxides of chromove. Oxides of chromove. Oxides of chromove. So oxides of chromove means chromium oxide, Cr2O3, molybdenum oxide, WO2O3, and WO2O3 and chromove V. Chromove. So vanadium oxide V2O5. What is the trick there for aromatization reaction? Oxides of chromove supported over alumina gel. Supported over alumina gel means they will give you Cr2O3. So what they will give you? They will give you like this. Let's say this is given 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Hexane is given. Hexane is given. Cr2O3 supported over Al2O3 heating, or they can write MO2O3 supported over Al2O3 heating, or they can give you V2O5 supported over Al2O3 heating. They can give you any one of them. Let's say I'm taking Cr2O3 Al2O3. It means Cr2O3 is the catalyst which is supported over alumina gel. This is the meaning of this. What will happen? This is normal hexane. Normal hexane. Now, which aromatic compound you can make by using 6 carbon? Which aromatic compound you can make by using 6 carbon? Everyone can say, sir, benzene we can form. What you can form there? You can form benzene. Is it okay or not? Now come to the formula. Normal hexane, it is what? C6H14. What is the formula of benzene? C6H6. Means if I balance atoms, I can say left side we have 6 carbon, 14 hydrogen. Benzene has 6 carbon and 6 hydrogens. Means in this side we have what? 8 extra hydrogens. They are going to release as hydrogen gas, H2 gas. Clear or not? 4H2 is released. It means this reaction, what is the nature of this reaction? In this is a normal hexane, C6H14 is giving C6H6 and hydrogen is released, means this reaction is dehydrogenation reaction. This reaction is what? Dehydrogenation reaction. Release of hydrogen, dehydrogenation. Like binding of hydrogen is hydrogenation. So removal of hydrogen is dehydrogenation. This aromatization reaction is also known as reformation. This aromatization reaction is also known as reformation. Aromatization reaction is also known as reformation. This is clear or not? So now let's say heptane is given 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Heptane is given and they are giving Cr2O3, Al2O3 heating. Sometimes they will give only Cr2O3. But actually it is Cr2O3 supported over Al2O3 or MO2O3 supported over Al2O3 or V2O5 supported over Al2O3. They can give you any of these 3 reagents. How to identify? What is given there? 1, 2, 3, 4, 5, 6, 7. Normal heptane is given. Normal heptane is given. But what you are knowing, we have to make 6 carbon aromatic compound, that is benzene. So what we have to prepare? Benzene we have to prepare. But total carbon count is 7 na yaar, and benzene is having only 6. 1 extra carbon is there. This is going to bind as CH3. This is a formed. Now what will happen? Balance the formula, you will get hydrogen is released. So how to balance now? Heptane, C7H16. C7H16. Now this molecule, toluene, what we can observe there? How many carbons? 7 carbon. How many hydrogens? 1, 2, 3, 4, 5 plus 3, 8. C7H8. Left side we have 16 hydrogens. Right side we have 8 hydrogens in this organic molecule, means 4H2 gas is released. Again same thing. This is dehydrogenation reaction, and this aromatization is also known as what? Reformation. Okay, so let's solve this question. Let's say this is given. I am not writing hydrogen because this much time is not there. Let's say this is given. Let's say this compound is given. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is given. This is given. An examiner is saying Cr2O3 Al2O3 heating. Cr2O3 Al2O3 heating. How to find the product? What we can say? 1, 2, 3, 4, 5, 6. We have to make 6 carbon aromatic compound. Make 6 carbon aromatic compound, that is benzene. What you are observing? 3 4 position has 2 extra carbons na yaar. So give number there. 1, 2, 3, 4, 5, 6. What you are observing? 3 4 has extra carbons. So this is 1 extra carbon. This is 1 extra carbon. This product is formed. This is a way to find the product. Okay. Generally they will ask only 2 questions. Generally they are asking 2 questions. One for normal hexane and one for normal heptane. Normal hexane giving benzene and normal heptane is giving toluene. Is it okay or not? This is clear. Come to next reaction. Next is what? Pyrolysis. Name is the answer. Pyro means what? Heating. Lysis means what? Breakdown or breaking. Means breakdown of molecule. Breakdown of molecule by heating is what? Pyrolysis. Breakdown of molecule by heating is what? Pyrolysis. Now, 2 important examples are there in our syllabus for pyrolysis. One is C12 means C12H26. You are knowing formula of alkane CnH2n plus 2. So obviously C12 2n plus 2, so 12 into 2 24 plus 2 26. It is what? Normal dodecane. Normal dodecane. It is the main component of kerosene. Main component of kerosene oil. Now this is going for pyrolysis, means heating in the presence of catalyst, nickel, palladium or platinum. In this case they can ask catalyst also. What catalyst we are using for the cracking of main component of kerosene, that is what? N-dodecane. Answer is what? Nickel, palladium or platinum. How to find the product? Very easy. Very easy. Very easy. How to find the product? 12 months are there. In whole year we have 12 months now. So 12 months. So substrate you can guess it is C12. Obviously CnH2n you have to follow. So you get complete formula there. C12. Products are C5 and C7. How to guess the product? Major product. So many products are formed. This is major product. Then how to find the products? Very easy. 12 months, one part. 7 days in a week. 7 days in a week. 12 months. So substrate is decided. Substrate is decided. Then 7 days in a week. So C7. So obviously total counting must be 12 na yaar. If one is 7, anyone can say this will be C5 yaar. Anyone can say na yaar, if this is C7, this will be C5. 5 plus 7 is 12 yaar. Common sense. Okay. After this, how to find the nature? Means which one is alkane, which one is alkene. So after this we have to say one more thing. 12 months, 7 days in a week, and C7 is big brother. C7 is big brother, means it is alkene. Alkane has more hydrogens than alkene for same carbon. So what will happen? This is big brother. C7 is big brother, means it is ane, alkane. So formula CnH2n plus 2. So it will be C7H16. Is it okay or not? This is what ene means CnH2n. So C5H10. You can check plus 16. 10 plus 16, 26. Understood how to memorize or not? How to memorize? What is there in our syllabus? Cracking. This pyrolysis is also known as cracking. Pyrolysis is also known as cracking. What is it there in our syllabus? 12 months. 12 months. 12 months break into 7 days in a week. So C7, C5 is formed. 7 is big brother. 7 is big brother, means it is alkane. Another one is alkene. In this way you can memorize. In this way you can memorize. So what is the important point there? Main component of kerosene is dodecane. Main component of kerosene is N-dodecane. It is going for pyrolysis in the presence of nickel, palladium, platinum. Going to give C5 and C7, 7 days in a week. 7 is big brother, so alkane. Obviously C5 is alkene. This is one cracking. Another cracking is C6, C6H14, hexane. What are the possible products? What are we are going to heat? We are going to heat, it is going to break. We are going to heat, it is going to break. In this case, and don't think that these are the only two products. These are the major products. Like we have 12 carbon chain. You can break from any position na yaar. This is most common fragments which you are getting during the pyrolysis of C12H26. Now come to this one, C6H14, possible products. C6, C6, C4, C3, C6, C6, C4, C3, C6, C4, C3, C6H14, C6H14, normal hexane giving 6, 4, 3. Sir, this is C6, this is also C6. How it can be different? This is alkane, this is alkene, so it is different. This is alkane, this is alkene, so it is different. So it means this is what? C6H, CnH2n na yaar. It means it is C6H12. This is a 14, this is a 12, means hydrogen is released. This is one possibility for this one. Now, after knowing this, we can write another also. C6, I said C6, C4, C3. This is in, this is also in, this is also in. In. This is C4. So obviously another fragment will be C2 or lower fragment will be C2. This is C3. So lower fragment will be C2 and much more lower fragment will be C1. Why sir 3 to 1? Because total counting is 6 na yaar. Total counting is C6. So we have to satisfy this one. So how to memorize? How to memorize? Very easy to memorize. Yeah, listen carefully. 6, C6, C4, C3. This is in. This must be in. This is in. This is in. This is in. This is C4. So another is C2. Total count is 6. This is C3. So lower fragment is C2. Next fragment will be C1. So 3 plus 2 plus 1, 6. 4 plus 2, 6. 6. Understood not? Now, if this is in, so formula will be what? CnH2n. It means H8 na yaar. Total hydrogens are 14. 8 done. So how many left? 6. So C2 has 6. 8 plus 6, 14. Satisfied? This is also in. It means it is also CnH2n. It means it is what? C3H6. Now C2, it is difficult to guess. Difficult to guess. Now we are not knowing it is ethane, ethene or acetylene. We are not knowing this. But C1 is very easy to guess here. C1 is very easy to guess. With one carbon, what do you have? You have methane na yaar, CH4. In 2 carbons, difficult to guess that it is alkane, alkene or alkyne. But 1 carbon is definitely methane na yaar. So what we can say, 6 plus 4, 10. This is a 14. 6 plus 4 done. 10 is done. What left? 4. So it is C2H4. Is it okay or not? This is a way to memorize all the pyrolysis products of C6H14. Okay, I'm going to write one more time. What is there? C6H14. If there is a confusion, CnH2n plus 2 you have to satisfy. Okay or not? Possible products. C6, C4, C3. C6, C4, C3. This is in. So this must be in na yaar. This is in. So the lower one is in. This is also in. This is C4, so this is C2. This is C3, so this is C2 plus C1. 3 plus 2 plus 1, 6. This is, now you have to write the formula there. This C1 you can guess it is C1 means CH4. In you can write the formula. This C2 you can write by balancing the hydrogens. This is about the cracking. Now controlled oxidation. In this case, one important case is there, oxidation of 3 degree hydrogen of alkane. You must know one thing. In case of alkane, if we have 3 degree hydrogen, that can be oxidized by strong oxidizing agents. For example, KMnO4. 3 degree hydrogen can be oxidized by strong oxidizing agent and it is oxidized into alcohol. If 3 degree hydrogen is there, it can be oxidized by KMnO4 into alcohol. This is oxidation of 3 degree hydrogen of alkane. This is for alkane. Is it okay or not? For example, if they are asking which of the following alkane can be oxidized, which of the following alkane can be oxidized by KMnO4, which of the following alkane can be oxidized by KMnO4. Now these alkanes are given and I am asking which of the following can be oxidized by KMnO4. So what I said, those alkanes who are having 3 degree hydrogen, those alkanes which are having 3 degree hydrogen can be oxidized by KMnO4 into alcohol. Now come to first one. This hydrogen is 1 degree. This hydrogen is 2 degree. There is no 3 degree hydrogen. It cannot be oxidized by KMnO4. This hydrogen is what? 3 degree hydrogen. Right? This hydrogen attached to this carbon and this carbon attached to 3 carbons. Obviously this carbon is 3 degree carbon and related hydrogen is 3 degree hydrogen. Means this can be oxidized by KMnO4. In this case, this hydrogen 1 degree, this is 2 degree, and this carbon is not having any hydrogen. This carbon is not having any hydrogen. This hydrogen is 1 degree and this is not having any hydrogen. Means this is the alkane which can be oxidized by KMnO4. What final thing is there? Say with me, those alkanes who are having 3 degree hydrogen can be oxidized by KMnO4. Can be oxidized by KMnO4 into alcohol. Now come to the preparation of alkene. So now we have alkyne. RC triple bond Cr. We are treating with H2 NiPd or Pt. Let's say Pd. What will happen? This alkyne is reduced into alkane. Now we want to stop this reaction at alkene. Listen carefully. H2PD is reducing alkyne up to alkane. Sequence of reduction is what? Alkyne reduced into alkene, alkene reduced into alkane. This is a sequence of reduction reaction. Now we want to stop this reaction at alkene. So what is required there? We have to decrease the activity of this catalyst palladium. If you decrease the activity of this palladium catalyst, if you decrease the concentration of or pressure of hydrogen gas, you can stop the reaction at alkene. So how to decrease the activity of catalyst? Take palladized charcoal poisoned by barium sulfate or quinoline. Take palladized charcoal poisoned by barium sulfate or quinoline. Or you can take PdCaCO3 also. So what will happen? This barium sulfate, this quinoline, this calcium carbonate, they are going to act as a poison. This barium sulfate, quinoline or carbonate. Due to these poisons, what will happen? Activity of catalyst get decreased. Listen carefully. What I am saying, if I use H2PD, very active catalyst, it will reduce up to alkane. But we want to stop reaction at alkene. For that, we have to poison it. We have to add poison there. So in the presence of poison, activity of catalyst is going to decrease and reaction can be stopped at alkene. So what will happen? This alkyne is reduced only up to alkene, and this alkene which is formed there is cis alkene. Which alkene is formed there? It is what? Cis alkene. Sir, why is this? Very easy to understand here. Very easy to understand. What is the concept there? From hydrogen and its compound you are knowing this nickel, palladium, platinum. They are having very high affinity towards hydrogen. They are having very high affinity towards hydrogen. They can absorb ADS, absorb large quantity of hydrogen there. So this palladium, obviously it is poisoned in this case by barium sulfate or quinoline. It is going to absorb hydrogen like this. This hydrogen is absorbed. I am just writing one representation to explain the cis product, why cis is formed. So this hydrogen is absorbed. Now alkyne is coming for reduction. So you can easily understand there, this hydrogen is absorbed. This hydrogen and this hydrogen can bind to this carbon from one side only, na yaar. Other side is palladium. It is like this. Let's say this is the surface of palladium. Assume this is hydrogen molecule. It is absorbed there. It is absorbed there. This triple bond, alkyne is coming. So what will happen? This alkyne can bind with these two hydrogen atoms from only one side, na yaar. Other side, we cannot place anything there. It is metal there, other side. It means hydrogen is absorbed. This is hydrogen absorbed on the surface. Triple bond is coming to get reduced. Hydrogen can bind only from one side, na yaar. It means you can prepare only cis alkene if there is a possibility of cis alkene. Sir, why you are saying if? For example, this is given RC triple bond CH, condition is H2PD CaCO3 or H2PD-C poisoned by barium sulfate. This is given. In this case, alkene is formed RCH double bond CH2. Can you say this is cis or trans here? There is no GI na yaar. These two hydrogens, these two atoms are same. HH, how we can say this is cis or trans? There is no concept of cis or trans for this alkene here. That's why I'm saying cis alkene is formed by H2PDC poisoned by barium sulfate or quinoline or calcium carbonate if there is a possibility of cis. Someone is taking terminal alkyne and asking, this will give you, and you just mug up the concept, okay, PDBSO4 cis, PDBSO4 cis, and they are saying terminal alkyne even though you are going to cis alkene. Wrong na yaar. If alkyne is a terminal, how we can get cis or trans here? Cis and trans meaningless, na? GI is not there. If internal alkyne is given, yes, now you can say in these cases you will get cis alkene. This is clear. Okay, come to next one. Monohalide to ene means we have to prepare alkene from monohalide. For example, I am going to take CH3, CH2, CH, CH3Cl. This monohalide is there. Now this monohalide is treated with, alcoholic NaOH or KOH. Sometime alcoholic NaOH, KOH, they will write like this, KOH or some alcohol, for example ethanol, or they can take any other alcohol. In this alcoholic KOH, what will happen? Alcoholic KOH is acting as base. It is acting as base. Alcoholic KOH is acting as base. Alcoholic KOH is acting as base. What will happen? It is known for beta elimination. Alcoholic KOH is known for beta elimination. Listen carefully. Alcoholic KOH is known for beta elimination. It is saying, if halide is there, I will remove beta hydrogen. If alkyl halide is there, I will remove beta hydrogen. Now, this is our leaving group. This is alpha. This is beta. This is also beta na yaar. Now, alcoholic KOH is saying, I am going to act as base. I am going to act as base. I will remove beta hydrogen. I will remove beta hydrogen. So this is one beta hydrogen. This is another type of beta hydrogen. I am not satisfying the balance. You can understand. Now this is one beta hydrogen. This is another beta hydrogen. So this alcoholic KOH can remove this beta hydrogen as well as it can remove this beta hydrogen. Let's say this is possibility number 1. This is possibility number 2. If I remove this beta hydrogen, double bond form at this region na yaar, Cl is leaving. If I go with this double bond form in this region, Cl is going to leave. It means you have two possibilities. One product you can form CH3, CH double bond, CH, CH3. Another product you can form CH3, CH2, CH double bond, CH2. Now what is the chemistry of alcoholic KOH? Listen the chemistry of alcoholic KOH. Alcoholic KOH is saying I can remove any beta hydrogen of monohalide or alkyl halide. I can remove any beta hydrogen of alkyl halide. So better to remove beta hydrogen who is giving more stable alkene. Listen carefully one more time. Alcoholic KOH is saying I am very powerful base. I can remove any beta hydrogen of alkyl halide. So it is better to remove beta hydrogen who is giving more stable alkene. Now out of these two, which alkene is more stable? This alkene has 3 plus 3, 6 alpha hydrogen. This alkene has 2 alpha hydrogen. This is more stable alkene. So this is a major product and obviously this is a minor product. Now one rule is there. If more stable alkene is formed as a major product, it is known as Sedgev product. It is known as Sedgev product. Now few of you might be thinking, sir, you are saying Sedgev but you are writing ZSF. Sir, you are saying Sedgev and you are writing this ZAITSEV because name is this, pronunciation is this. So this Sedgev is actually pronunciation, name is ZSF. So examiner can give you both. It is also written in NCERT. Okay, and if less stable alkene is formed as major product, that is known as Hoffman product. What is the chemistry of alcoholic KOH is clear. Well, I will take one more example so we'll understand the concept. Let's say this is given. Let's say this is given. It is treated with alcoholic KOH. What is the chemistry of alcoholic KOH? What alcoholic KOH is saying? Alcoholic KOH is saying I am able to remove, listen carefully. Alcoholic KOH is saying I am able to remove any beta hydrogen of alkyl halide. I am able to remove any beta hydrogen of alkyl halide. So better to remove beta hydrogen who is giving more stable alkene. Now, this is our leaving group. This is alpha, this is beta, this is beta, this is beta. Okay, let's say for this one I am writing beta H1, I am writing for this one H2, and for this I am writing H3. So alcoholic KOH is acting as base. It can remove this H3, it can remove this H2, it can remove this H1. Which one is giving more stable alkene? Let's say we removing this H1, double bond form at this region, na? So product will be this C, double bond. This Cl is obviously removed, double bond. Then this carbon, this C, this carbon, this is formed. If I remove double bond, if I remove this hydrogen, double bond form at this position, na? What product will be there? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3 position, 1, 2, 3 double bond is formed in this region. Likewise, if I remove this H3, double bond form in this region. 1, 2, 3, 4, 5, 6. 1, 2, 3. There, double bond is formed there. And this is CH3 there. Okay. Now, first alkene, it has, this is CH3, this is CH2, this is CH2. It has 3 plus 2 plus 2, 7 alpha H. This has 3 plus 2 plus 2, 7 alpha H. This alkene has 4 alpha H. So these two could be major products. Is it okay or not? So thing is that what alcoholic KOH is saying, I am able to remove any beta hydrogen. So better to remove beta hydrogen who is giving more stable alkene. Keep it simple. Now come to this vicinal dihalide is there and we want to prepare alkyne from this. As well as we want to prepare alkene also. I will select one reagent zinc. From this vicinal dihalide I want to prepare alkene or alkyne. First of all I am writing zinc. I don't know chemistry. What product will form? I don't know. No problem. No problem. I am knowing one thing. Zinc is hungry for 2 halogens. Zinc is hungry for 2 halogens because it is saying if 2 chlorines are there, I will make ZnCl2. Zinc is hungry for 2 halogens and zinc will say now 2 chlorines present in same molecule. 2 chlorines present in same molecule. I will remove both chlorines. I will remove both chlorine atoms and I will remove them at ZnCl2. What will happen? Double bond is formed there. What product is formed? RCH double bond CHR. So if you have vicinal dihalide and you want to prepare alkene, what do we have to select? Zinc dust. Common sense. Now, we have this. Now what will happen? What will happen if it is treated with alcoholic KOH? Alcoholic KOH. Alcoholic KOH, same thing. It is saying I am base. I am going to remove beta hydrogen. This is a leaving group. This is alpha. This is beta. This is beta hydrogen. I will remove this beta hydrogen. After removal of this beta hydrogen, what product is formed? RC. This become double bond R. This Cl is there and this is there. This is formed. Chloroalkene is formed. Now, alcoholic KOH. Now, this hydrogen, this beta hydrogen, this is leaving group, alpha, beta. This beta hydrogen is attached to sp2 carbon. It is attached to sp2 carbon. So, strength of this carbon bond is more than the previous one. As well as this chlorine has partial double bond character. So, this alcoholic KOH is not able to remove this hydrogen attached to sp2 carbon. This alcoholic KOH is not able to remove this hydrogen attached to sp2 carbon. Alcoholic KOH is saying, I can remove beta hydrogen of alkyl halide in which hydrogen attached to sp3 carbon. But my power is not enough. Alcoholic KOH is saying my power is not enough to remove beta hydrogen of chloroalkene. Chloroalkene means hydrogen attached to sp2 carbon. So we need, so this is not going to proceed further. So we need dangerous base. Dangerous base means base who is stronger than alcoholic KOH also, and that is NaNH2. That is NaNH2, sodamide. Sodamide will say, my friend alcoholic KOH, you are not able to remove this beta hydrogen. No problem, I will remove. I am more dangerous than you. I am more dangerous than you. So this sodamide is going to remove this beta hydrogen. What will happen? This is going to release and you can observe this is a formed. Okay or not? So what we can conclude? What we can conclude? If you have, now this is final thing. This is final thing. If you are not knowing mechanism, there is no problem. You must know these 3 important points there. Vicinal dihalide is there. Treated with zinc dust. What will happen? Zinc dust is saying I am hungry for 2 halogen na yaar. two halogens. I will take both halogens. Double bond will form there. Product will be what? RCH double bond CHR. Alkene is formed. This is treated with alcoholic KOH. Alcoholic is saying I am going to remove beta hydrogen. I am going to remove beta hydrogen. What will happen? RCCl. This is removed. RC double bond C. This is formed. This is H. This is Cl. This is formed. But alcoholic is saying I cannot remove hydrogen from this. So now if it is taken like this, alcoholic KOH followed by the addition of sodamide, or directly sodamide is taken. Sodamide is taken. What will happen? Vicinal dihalide will give you alkyne. Alcoholic is followed by sodamide is given, or only sodamide is given. Vicinal dihalide will give you alkyne. This is way to prepare alkyne from vicinal dihalide. So what we can conclude, if we want to prepare alkene from vicinal dihalide, select zinc. And if you want to prepare alkyne from vicinal dihalide, select alcoholic KOH followed by sodamide or sodamide. What will happen? Alkyne will form. Next, electrophilic addition reaction. Very important reactions are there. I will explain through only one substrate. You will understand all the concepts of electrophilic addition reaction. This is there. Now it is treated with HCl. So HCl you can break like H plus Cl minus. Now this double bond has two possibilities. This double bond you can break like this, one possibility. Another possibility, this double bond you can break like this. Two possibilities are there. If I am breaking double bond like this, this become plus, this become minus. Minus immediately bind with H plus. So for HCl also you can, for simplicity, HCl you can write like H plus Cl minus. So it become easier for you. Minus immediately bind with plus. What will happen? One possibility, you will get this CH3 CH plus CH3. Second possibility, you are breaking like this, minus form in this region, plus is this region. Minus immediately bind with H plus. So what will happen? This become CH3 CH2 and this becomes CH2 plus. Which plus is more stable? This plus is more stable. No? It has 3 plus 3, 6 alpha H, it has only 2 alpha H. It means this is going to give major product. Okay or not? So if they are giving you alkene with HX, make most stable cation around double bond. Means for the carbon related to double bond. And according to that you have to go for the reaction. Now what will happen? So now what we can say there? We have this CH3 CH double bond CH2. Examiner is giving HX. I will write like this, H plus X minus. Plus is more stable on this carbon because this plus is stabilized by more number of alpha H. So minus must have developed on this carbon. Break bond like this, minus bind with plus. What will happen? This is going to give CH3 CH CH3 plus. Next, this cation is already stable in this case. We cannot rearrange this. What will happen? X minus is going to bind there. This product will form CH3 CH X CH3. One case. Second case. This is given. CH3 CH double bond CH2. They are giving dilute sulfuric acid. Dilute sulfuric acid means we have large quantity of water and very small quantity of sulfuric acid is added there. So dilute sulfuric acid means what? Large quantity of water and very less quantity of sulfuric acid. Means actually it is a reaction of water. That's why sometimes it is written like this, H2O H plus, or sometimes they are writing like this also, H3O plus. Now what will happen after this? It is very easy. Once you know dilute sulfuric acid means actually it is the reaction of water. After knowing this, you can simply solve this reaction. You will say this is there CH3 CH double bond CH2. They are giving dilute sulfuric acid. Immediately you can write H plus H2O. Now same logic, plus is more strong on this carbon now. Plus is more strong on this carbon now. So what will happen? We have to break bond like this. Minus immediately bind with plus. Minus immediately bind with plus. What will happen? This becomes CH3 CH plus CH3. What will happen next? H2O is going to attack. Nucleophile is H2O. So H2O is going to attack. What will happen? This is going to give CH3 CH CH3. Okay, or I will give you one simple trick also. One simple trick I will give. This nucleophile, in this case, actual nucleophile is H2O. If someone is asking what is the nucleophile there, answer is what? H2O is the nucleophile there. What is our trick? Break H2O into H plus and OH minus. If I am breaking water like this, it is a trick. Because actual nucleophile is H2O. Bind OH minus to this plus. This is formed. Understood or not? Next, ozonolysis, very easy to find. Ozonolysis, what will happen? Let's say this is given RCH double bond C RE. This alkene is given. Now they are giving O3, then H2O in the presence of zinc. First ozone, then H2O in the presence of zinc. How to find the product? Very easy to find the product. Double bond is there, break double bond. Bind oxygen. What will happen? This become RC double bond OH. This also becomes same RC. So 2 moles of this is formed. RC double bond OH. Now since zinc dust is there, we cannot oxidize this aldehyde further. Zinc dust is there, so you cannot oxidize this aldehyde further. Means this is your final product. I will take some better examples for more clarity. This is given. Examiner is saying O3 H2OZN. Break this bond, bind oxygen. So what we have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 carbon is there. Okay, 6 carbons are there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 carbons are there. Oxygen is bonded to 1 and 6. So this become what? Double bond O. 1 valence is left, that is satisfied by hydrogen. Likewise, there also this is 6th carbon bonded with C double bond O, valence is satisfied by hydrogen. This product is formed. This is way to find the this ozonolysis product. Let's say benzene is given. One more example we'll take for more clarity. Benzene is given. Same condition, O3, second H2OZN. How to find the product? Whenever they are giving any molecule where resonance is present, so answer by writing resonating structure. For example, if I write resonance structure of benzene, this is the resonance structure of benzene. Now what is our trick? Break double bond, bind oxygen. Break double bond, bind oxygen. Now what you can observe there, this bond is intact na yaar. This bond is not going to break. It means this part is giving what? Observe please. Oxygen double bond. This one carbon is there. Oxygen double bond carbon. Single bond. This carbon double bond oxygen. Hydrogen. If you observe, this part is also same as this and this part is also same as this, means this is giving 3 moles of this. This is way to find ozonolysis. For ozonolysis, what is the identification there? They will give you O3 followed by addition of H2 in the presence of zinc dust. Okay or not? Zinc dust is there, don't oxidize aldehyde further. How to find the product? Break double bond, bind oxygen. This is the concept for ozonolysis. Now, preparation of alkyne from CaC2 and vicinal dihalide. Vicinal dihalide is discussed. Just now we discussed vicinal dihalide. Vicinal dihalide is there. Vicinal dihalide is there. I want to prepare alkyne. What I will use? I will use alcoholic KOH, alcoholic which followed by the addition of sodamide, or I can directly use sodamide. From calcium carbide is given. Calcium carbide means what? CaC2. CaC2 means calcium 2 plus, C2 2 minus. Ca2 plus, C2 2 minus. Add water, H2O. So for water, you can write like this, H plus OH minus. Now after this, even class 9th student can solve. H plus, obviously plus bind with minus. This is 2 minus. How many H plus required? 2H plus. So plus and minus going to combine. 2 plus 2 minus, what is formed? C2, H2 is formed. By C2, 2 minus is there, so 2H plus required to neutralize the charge. C2, H2 is formed. Calcium plus 2, OH minus 1, so 2 OH minus required. So what products are formed? Calcium hydroxide and C2H2. C2H2 is what? Acetylene, HC triple bond, CH. So two important reactions are there for alkyne. One is preparation of alkyne from CaC2, another is from vicinal dihalide. Next, reaction of alkyne with dilute sulfuric acid and hydroboration oxidation reaction. These two are the very important reactions. Okay, we'll cover one by one. Now this alkyne is there, RC triple bond CH is there. It is treated with diluted sulfuric acid in the presence of Hg2 plus catalyst. Now how to find the product? Very easy to find. Now we can have two possibilities. If I break this bond, I will get plus on this carbon like this. Second possibility, if I break this double bond, like this, I will get plus on this carbon. Now you have to think where plus is more stable, number 1 or number 2. Plus at number 1 stabilized by hyperconstant of this R group na yaar. It means plus is more stable at number 1. If plus is more stable at number 1, obviously we will make plus at number 1 na yaar. Means I wrote number 1 for this, number 2 for this, according to that one. Okay. So now we are knowing plus is more stable on this carbon. Plus is more stable on this carbon. So what will happen? I will break like this. So this become minus, this become plus. Sulfuric, dilute sulfuric acid. Just now we discussed dilute sulfuric acid means reaction of water. So what we can write? H plus H2O minus bind with plus. Minus bind with plus. Common sense here, obviously minus will bind with plus. What will happen? This carbon is there. Now double bond is there. This becomes CH2. Now this is a plus. Next, H2O is the nucleophile there. What is our trick? Break water into H plus OH minus. This is the trick. What will happen? Minus bind with this plus. What is formed? RC. Double bond CH2. This is OH. Now if you observe carefully, this is in, this is all. Can you say this is enol? This is in, double bond. This is alcohol, all, enol. Tautomerizing. Enol is going for tautomerism. So this is going to tautomerize. If it is going for tautomerism, what will happen? What is the simple way to find the product of tautomerism? Double bond become single bond. Single bond become double bond. Double bond become single and single become double. So what will happen? You will get this RC double bond O CH3. Observe carefully. This was single. Now this become double. This was single. This was double. Now it become single. This is a way to find product of tautomerism directly. Double bond become single bond. Single bond become double bond. This is a way to find the tautomerism. Okay or not? Next reaction. This is given. Same substrate I am taking, CH3, C triple bond, CH is there. It is treated with B2H6, B2H6 THF followed by addition of H2O2OH minus. Now logic, plus is more stable on this carbon. Why? Stabilized by hyperconstant of this alpha H, more alpha H. Obviously we have to break like this minus. B2S6 break like BH3. B2S6 we have to break like BH3. What we can say in B2S6, it is going to break like BH3. Boron is plus, hydrogen is minus. Listen carefully. Boron attached to hydrogen and boron attached to carbon. In these cases, boron has a plus charge and hydrogen or carbon, they have negative charge. Boron attached to hydrogen, boron attached to carbon. In these two cases, if you can, these are most important cases for organic chemistry. Boron has a plus, hydrogen, carbon, they are having negative. So now what will happen? Minus going to bind with this plus here, common sense, and minus is going to bind with this plus. Minus bind with plus, minus bind with plus, common sense. What will happen? You will get this CH3, this H is bonded there, you will get this CH, this become double bond, CH. See this CH3C, this triple bond is going to break, so double bond left, H bonded to this becomes CH3CH, CH, and this boron is there. Now two more hydrogens left, na? Two more hydrogens left. So this reaction is repeated 2 times. So what will happen? Same, this you can get total 3 units. How to find? Find first one and write 3 times. That is all. Now, after this, what is added there? H2O2 is added. H2O2 is added. H2O2 is added in the presence of OH minus. Boron is plus, carbon is minus. H2O2 is there, OOH I can write like this. So this H2O2 I can write O plus, O minus. What will happen? This minus bind with this plus. Minus bind with this plus. Minus bind with this plus. It is not binding with this OH minus. Minus minus cannot bind there, common sense. What will happen? This minus bind with this OH plus of hydrogen peroxide. So what is formed there? CH3, CH double bond, CH, OH. Again, this is what? Ene. This is all. It has to tautomerize. After tautomerism, what you will get there? CH3, C, H2, C double bond, OH. Double bond becomes single, single bond become double. Now I am going to conclude both the reactions. What is important for you? Finally, what you have to know? This alkyne is given. This alkyne is given. One condition, they are giving dilute sulfuric acid or they are giving H plus H2 or H3O plus. Second condition, they are giving B2H6 in the presence of solvent THF followed by addition of hydrogen peroxide in alkaline medium. These two conditions are very important. These two conditions are very important. Now, if this is given, plus is more stable on this na yaar. This plus is more stable na. So bind OH to more stable one. Okay, so what bind OH to more stable one. So what will happen? CH3, CH, OH, double bond, CH2. It is going to tautomerize. After tautomerism, you will get this CH3, C double bond, O, CH3. This is the final thing for you. B2S6 is given. Just opposite. Plus is more stable on this. It is less on this, the bind OH there. So what will happen? You have to bind OH to this place. Opposite of this reaction. What will happen? You will get this CH3, C, H double bond, CHOH. In all, again it is going for tautomerism, same as previous condition. After tautomerism, what will happen? You will get product CH3, CH2, C double bond O, H. What is there? What trick is there? Double bond becomes single, single bond become double. So these two are the most important reactions for alkyne. Alkyne reacting with sulfuric acid, dilute sulfuric acid, obviously. Dilute sulfuric acid, bind OH to the plus where it is more, bind OH to the carbon where plus is more stable. And B2S6 THF opposite of this. Clear or not? This is known as, this complete reaction is known as hydroboration oxidation reaction. Next one, benzene. How to prepare benzene? All are known to you. This is what? 1, 2, 3, 4, 5, 6. This is a normal hexane. Just now we discussed normal hexane to benzene aromatization. What we have to select? Oxide of chromium supported over alumina gel, or oxide of MO2 molybdenum supported over alumina, or oxide of vanadium supported over alumina. High temperature, high pressure, you will get this aromatic compound benzene. PHCOOH. PHCOOH means what? Benzoic acid is there, and you have to prepare benzene. Which reaction? Decarboxylation reaction. NaOH plus CaO heating. And this is very important. You have phenol, and you want to convert phenol into benzene. Means you want one reagent which can eat this oxygen. So zinc dust is having tendency to eat this phenolic oxygen. Zinc dust will eat this phenolic oxygen. So if zinc dust eat this oxygen, what left? Hydrogen attached to this carbon, benzene is formed. So if you want to convert phenol into benzene, you have to add zinc dust. And if you want to convert acetylene into benzene, we have to take red hot Fe tube. What we have to take? Red hot Fe tube. If you want to prepare benzene from acetylene, you have to take what? Red hot Fe tube. These are the important reactions for preparation of benzene. Now come to electrophilic substitution reaction. Very easy. Benzene is given. Now they are giving few important reactions I am going to write. They are giving HNO3 plus H2SO4. HNO3 plus H2SO4, one reaction. They are giving H2SO4, another reaction. Let's say they are giving Br2 FeBr3. Third reaction, I will write more. Let's say they are giving normal propyl chloride with AlCl3, Friedel Crafts alkylation. They are giving RC double bond OCl, acid halide with AlCl3, Friedel Crafts acylation. Now, how to find the product? Very easy. First case, HNO3 plus sulfuric acid. HNO3 sulfuric acid, this is going to generate electrophile NO2 plus. This is going to generate electrophile NO2 plus. NO2 plus electrophile is generated by HNO3 plus H2SO4. This NO2 plus is going to bind with this benzene. What product is formed? Nitrobenzene is formed. What product is formed? Nitrobenzene is formed. H2SO4. This is going to generate electrophile SO3. This SO3 is going to bind with benzene. Then product will be what? SO3H, benzene sulfonic chloride. Now, benzene sulfonic acid. Br2 FeBr3. This is going to generate electrophile Br plus. So Br plus is going to bind with benzene. What product is formed? Bromobenzene is formed. What product is formed? Bromobenzene is formed. Now, this is very important reaction. Now, this is given normal propyl chloride. Normal propyl chloride is given, treated with AlCl3. AlCl3 is Lewis acid. It is going to bind with Cl minus. What will happen? Cl minus is bind with this AlCl3. What will happen? This carbon is formed. This carbon we rearrange to this position. Na? This carbon is rearranged to this position. Now, this is our final electrophile. This is our final electrophile. Firstly, Cl minus bind with AlCl3. So after removal of Cl minus, plus charge generated on this carbon, plus rearranged to this position, this plus is formed. Then this plus, this electrophile is going to bind with this benzene molecule. What will happen? This product is formed, named as cumene. This is very important molecule. Why it is very important? Because it is used in the industrial preparation of phenol. Very important molecule. In this case, same. Cl minus going towards AlCl3. So Cl minus removed. What left? RC double bond O plus. This electrophile is formed. This is going to bind with benzene ring. What product will be there? This C double bond OR is formed. So these are few important electrophilic substitution reactions of benzene. Treating with HNO3 H2SO4, nitration. Sulfuric acid, sulfonation. Br2 FeBr3, bromination. Alkyl halide with AlCl3, Friedel Crafts alkylation. Acid halide with AlCl3, Friedel Crafts acylation. Okay, so these are important reactions. Now, one very important case is there for benzene and chlorine. One case, they are giving Cl2 AlCl3. Second condition, they are giving Cl2AlCl3, where this Cl2 is taken in excess. And third condition, they are giving Cl2H nu. These three are the very important reactions for benzene. Benzene is treated with Cl2AlCl3, first case. Benzene treated with Cl2 excess AlCl3, Cl2 chlorine is taken in excess, and third Cl2H nu. First case, Cl2AlCl3, what will happen? Electrophile Cl plus is generated. Product, chlorobenzene is formed. Chlorobenzene is formed. But now they are taking chlorine in excess. Chlorine in excess, what will happen? Electrophilic substitution reaction will happen in multiple times. After repetition of electrophilic substitution reaction, what will form? This is benzene. All 6 hydrogens of benzene are replaced by chlorine. This product is formed, which is known as hexachlorobenzene. This is known as what? Hexachlorobenzene. Now, if they are giving Cl2H nu, they are giving Cl2H nu, what will happen? They are giving Cl2H nu. This pi bond is going to break and chlorine is going to bind there. One hydrogen is already there for each carbon. Chlorine is going to bind there. This product is formed. C6H6Cl6 is formed, which is known as benzene hexachloride. Benzene hexachloride is not having benzene. This is very important. Benzene hexachloride is not having benzene. Benzene hexachloride is not having benzene. Okay, now listen. Sometimes they will give like this. Benzene, Cl2AlCl3. Benzene is taken in excess. Obviously, monochloro will form. Chlorine taken in excess. Polychlorinated 6 chlorine will bind to benzene ring. All 6 hydrogens of benzene replaced and chlorine is going to bind there. And one more thing, these reactions we have to perform. These reactions, electrophilic substitution reaction of benzene in the presence of halogen, we have to perform in dark and cold conditions. Why? Because if it is light or if it is high temperature, it may go for this free radical reaction. This may go for free radical addition reaction. Is it okay or not? So they can ask this question also, like if you are doing electrophilic substitution reaction of benzene in the presence of chlorine, bromine like this, then we have to perform reaction in presence of light or in dark. Answer is ESR reaction. You have to perform ESR reaction. You have to perform in dark, because if you take Cl2H nu, it is going to give you free radical, and that is going to give you product benzene hexachloride, and benzene hexachloride is not having benzene. Come to next one. Geldahl's method. Geldahl's method. Now, Geldahl's method is used for the estimation of nitrogen present in the organic compound. Geldahl's method is used for the estimation of nitrogen present in the organic compound. Geldahl's method is based on, or its chemistry is based on ammonia gas which is liberated during the reaction. Its chemistry is based on the ammonia gas liberated during the reaction. What is the reaction there? We are taking one tube which is known as Geldahl's tube. In this tube we are placing organic compound plus sulfuric acid plus copper sulfate. What will happen? Organic compound is liberating ammonia gas, ammonia combined with sulfuric acid, giving ammonium sulfate. Giving what? Ammonium sulfate. This is the theoretical part of Geldahl's method. That's why they can ask one question. In Geldahl's process, or Geldahl's method, what we are taking in Geldahl's flask? Answer: we are taking organic compound with sulfuric acid and copper sulfate. Organic compound with sulfuric acid and copper sulfate. And one more question they can ask: what is the role of copper sulfate? What is the role of copper sulfate in Geldahl's method? Answer is: it is a catalyst. It is the catalyst in Geldahl's method. They can ask, what is the role of copper sulfate in Geldahl's method? Answer is: copper sulfate is going to behave like catalyst. This is the theoretical part. And one more point. Geldahl's method is not possible for nitro compounds, any nitro compound, Gildan method not possible. Those compounds who are having diiso, who are having nitrogen double bond, nitrogen means azo compounds. It is not possible for nitro compounds, it is not possible for azo compounds, and it is not possible for those molecules who are having nitrogen attached to ring. Those molecules in which nitrogen is the part of ring. Nitrogen is the part of ring. This is very important. Part of ring. For example, if I ask pyridine molecule is there and pyridine is there and aniline is there. Pyridine, aniline. Which case Gildan's method is possible? In this case possible, in this case not possible. What is the difference there? In this case nitrogen is the part of ring. In this case nitrogen is out of ring. So in this case Gildan's method possible, in this case not possible. For example, if I take this molecule, for this molecule Gildan's method not possible. For this molecule not possible. Nitro compound, no? Nitro compound not possible. But if it is like this, let's say we have this compound. For the, yes, possible. Understood? So what final thing is that Gildan's method is not possible in 3 cases. One case nitro compound, second case azo compound, and third and the most important one, nitrogen is present in ring. Nitrogen is present in ring means nitrogen is the part of ring. In these 3 cases Gildan's method is not possible. Now come to the numerical. Numerical is very easy. Numerical part is very easy. For example, let's say it is given we have 20 gram of organic compound, 20 gram of organic compound. It is heated in Gildan's flask and liberated NH3 gas, ammonia gas is absorbed by 2 molar 100 ml H2SO4. Remaining sulfuric acid is neutralized by, let's say, 1 molar 100 ml NaOH. We have to find the percentage of nitrogen. Now, if you are observing carefully, you can solve the question without any formula, just by balancing the reaction, just by the basics of your mole concept, you can solve questions of Gildan's method. Now listen, what they are saying, now we have to observe 3 important data there. 20 gram of organic compound, sulfuric acid is given 2 molar 100 ml, and sulfuric acid neutralized by, remaining sulfuric acid neutralized by 1 molar 100 ml NaOH. Now listen. What is the principle there? Ammonia is there. We are adding sulfuric acid in a known excess. Known excess means we are knowing what amount is added there, but we are adding in excess. So some sulfuric acid will left. That left sulfuric acid we are neutralizing by some base, for example NaOH. And after this we have to find the sulfuric acid which has reacted with ammonia. It is like this. Assume I am giving you 2000 rupee and I am saying, okay, go in the market and just enjoy, buy whatever you want to buy there. You are going in market, you are spending some money, you are coming back. When you are coming back, I want to ask how much money left, but I don't have dare to ask. Then I will ask in another way. Beta, how much money? Means like this, I am going to explain one more time, listen carefully. I am giving you 2000 rupee. I am giving you 2000 rupee. I am saying, oh, go and spend this money. You are coming back and I want to ask how much money you spent it. So I will ask in another way. What money left in your pocket? I'm not directly asking how much money you spent it there. I'm asking how much money left in your pocket. You say, sir, 500 left, sir. So I will calculate now 1500 you have spent it. This is what basic of Gildar's method. In this case, I am giving you some money, excess, and after that I am trying to find what money left. Remaining difference is what? Difference is actually reacted with ammonia. Difference is actually you spend it. So now focus on the data, you will get answer easily. Very easy to solve the questions of Gildar's method. Very easy. They are saying 2 molar 100 ml sulfuric acid is added. 2 into 100 means 200 millimole of sulfuric acid is added. But they are saying it is reacting, it is remaining is neutralized by 1 molar 100 ml NaOH. So write the balanced reaction of sulfuric acid NaOH, H2SO4 plus 2 NaOH is equal to product. I am not writing product. So 1 into 100 millimole of NaOH. 100 millimole of NaOH is actually reacting with sulfuric acid. Now you can easily find the sulfuric acid by balancing. 2 mole of NaOH means 1 mole of sulfuric acid. 100 millimoles of NaOH means what? 50 millimole. By 2, 1, half, 100, 50. So it means sulfuric acid is 50 millimole. This 50 millimole of sulfuric acid is left. Left will react with NaOH na yaar. It is left. I gave you 200 rupee. 50 rupee left in your pocket means you have spent 150, not 200 minus 50. So that is spent while reacting with ammonia. So what we can say, NH3 plus H2SO4. This is their balanced reaction. 1 H2SO4, so 2 ammonia, product, ammonium sulfate. This is what? 150 sulfuric acid is actually reacting with ammonia, na? 1 reacting, so 2 ammonia. 150, so 300 ammonia. It means 300 millimoles of NH3 is there. 1 NH3 has 1 nitrogen. So 300 millimole has exactly same nitrogen. So 300 millimoles of nitrogen is there, means 300 into minus 3 mole of nitrogen is there. Molar mass of N is N. Molar mass of N is what? 14, so multiply by 14. This is mass of nitrogen divided by mass of organic compound multiplied by 100 is the percentage of nitrogen. I will write one more question so you will understand. Let's say they are saying we have 20 gram of organic compound. It is heated in Gildar's flask. It is heated in Gildar's flask and liberated gas is absorbed by 3 molar 100 ml H2SO4. Liberated gas is absorbed by 3 molar 100 ml sulfuric acid, and remaining sulfuric acid is neutralized by let's say 2 molar 100 ml NaOH, and we have to find the percentage of nitrogen. Now you can easily say, sir, I am giving 300 millimole of sulfuric acid. 3 into 100, 300 millimole of sulfuric acid is given. So what will happen now? Remaining sulfuric acid is obviously reacting with NaOH, na? So it is reacting with NaOH. Balanced reaction is sulfuric acid plus NaOH is equal to product. This is how much? 100 into 2. NaOH is what? 200 millimole. NaOH is what? 200 millimole. You will say 2, so it is 1. 200, so it is what? 100 millimole sulfuric acid. 100 left. 300 was given, means how much is reacting with ammonia? 300 minus 100 means 200. 200 is reacting with ammonia. After this, we have to write the balanced reaction. NH3 plus H2SO4. It is 1:2. 1:2. Product ammonium sulfate. Sulfuric acid is 200 millimole. Sulfuric acid is 200 millimole, which is actually reacting with ammonia. So 1, so it is 2, so it is 400 millimole. 400 millimole of what? Ammonia. 1 ammonia has 1 nitrogen. So nitrogen is what? 400, exactly same millimole, means 400 into 10 power minus 3. This much mole is there. Mass of nitrogen 14 divided by mass of organic compound multiplied by 100. This is the percentage of nitrogen. This is all about Gildar's method. Okay. So most of the part of this class 11th basic organic chemistry is done. Okay, few more things are there, like methods of purification. In methods of purification, what is important? For example, simple distillation. Okay, we start from sublimation. For sublimation, principle is important. If organic compound is sublime and impurity is non-sublime, we can go for sublimation. They can ask directly principle. What is the principle of sublimation? Answer: organic compound is sublime. Organic compound is sublime and impurities are non-sublime. Then we can, if this condition is followed there, then we can go for sublimation. Crystallization. What is the condition there? Organic compound is having high solubility at high temperature. High solubility at high temperature, but it is having low solubility or it is sparingly soluble at room temperature. Then we can go for crystallization. If organic compound has high solubility at high temperature and solubility is low at room temperature, then we can go for crystallization process. This is the principle there. Simple distillation. If difference in boiling point is big, let's say one compound is A, another compound B, the boiling point is 100 degrees Celsius and 40 degrees Celsius like this, or let's say this is 100, this is 60 degrees Celsius. If big difference is there in boiling point, we can go for simple distillation. Example: chloroform and aniline, mixture of these two can be separated by simple distillation. So this is the important point. What is the simple distillation? Simple distillation is used when difference in boiling point is big. First important point. Second important point, example: mixture of chloroform and aniline can be separated by simple distillation. Fractional distillation. Fractional distillation. When we are using fractional distillation, if difference in boiling point is less, we have to go for fractional distillation. If difference in boiling point is less, we have to go for fractional distillation. In this case, we are using fractionating column. Example: different fractions of crude oil are separated by this method, is fractional distillation method. Means crude oil can be, means components of crude oil can be like crude oil components like petrol, diesel, kerosene. So many compounds are there, like xylene is also there. So many organic compounds are there in crude oil. All these components of crude oil can be separated by fractional distillation. Can be separated by fractional distillation. This is important point there in fractional distillation. Steam distillation. Two things are important: principle and example. For steam distillation, organic compound must be steam volatile. It must be what? Steam volatile but immiscible in liquid form. Means it is the friend of water vapor. It is volatile with water vapor. It is going with water vapor. But once it is converted into liquid, they are now immiscible. They are not soluble. This is the principle for steam distillation. Example: aniline from aniline water mixture is separated by aniline water mixture is separated by this method, steam distillation. So if they ask chloroform and aniline, they are separated by simple distillation. Aniline from aniline water mixture is separated by steam distillation. Okay. Next is what? Distillation under reduced pressure. So you are knowing, if we decrease pressure, boiling point is going to decrease. If we decrease external pressure, boiling point is going to decrease. See, if boiling point of compound is very high, or compound is going to decompose at its boiling point, then we are going for this process. Let's say some compound is there and that compound is going to decompose, they are going to break at its boiling point, then we cannot proceed for that simple distillation method, na? Because we are heating, we are giving temperature up to boiling point and compound is going to break. We cannot go for simple distillation. Or compound is having very high boiling point. Let's say 500, 600 degrees Celsius or 7, like this, very high temperature is there, boiling point is there. So for that very high boiling point, we have to consume large quantity of fuel there, na? In those cases, We are going for this process, distillation under reduced pressure. What are the conditions there? I am going to ask one more time. If boiling point of compound is very high, or compound is going to decompose at or just before that boiling point, at or below its boiling point, then we have to use distillation under reduced pressure. Example, glycerol is separated from spent soap and detergent. We are separating glycerol by this method. From spent lye, glycerol is separated by this method. Is it okay or not? This is what? Distillation under reduced pressure. This is all about methods of purification. So sublimation condition, organic compound is sublime, impurities are non-sublime. Crystallization, organic compound highly soluble at high temperature but having very low solubility, means sparingly soluble at room temperature. This is the condition for crystallization. Third condition, third example, simple distillation, difference in boiling point is big. Example, chloroform and lean can be separated by this method. Fractional distillation, if boiling point difference is low. Example, crude oil, different components of crude oil separated by this method. Steam distillation, this is very important case there. Steam distillation is applicable if organic compound is soluble, is steam volatile. It is a friend of water vapor. It is the friend of it, means they are saying if water vapor, organic compound, they are friends. They are going together in vapor phase. But once it get liquefied, they are going to make separate layers. They are going to make separate. They are now immiscible. This is the condition of steam distillation. And last one is distillation under reduced pressure. If boiling point of organic compound is high, then we have to decrease it by decreasing the pressure, or compound is going to decompose. In that case also, near to its boiling point, in that case also we are using this method. Example, glycerol is purified or extracted from spent lye by this method. This is all about important points of methods of purification. Okay, now revise all the concepts which I explained today and try to solve at least 40 to 50 questions for each topic. Like for alkane, 40 to 50 questions, alkene, alkyne, 40 to 50 questions. Method of purification, just read NCERT quickly. Okay, the last method also solve numerical problems of NCERT. One in-text problem is there and one question is there in exercise. Solve those two questions of NCERT. So what will happen, if any question is coming from this part, you can easily take. So revise those concepts which I explained today and after that solve the questions. Okay, bye bye, all the best.